Thank you very much, everyone, for logging in and attending this first of the ANFF webinar series entitled Enabled by ANFF. Throughout the series, we're trying to highlight some of the science and some of the projects that we are involved with and that we support, but looking at them from the point of view of some of the alignments that we have with research priorities and the areas of emerging industry focus that are coming from both our state and federal governments. This is a series of 6 webinars, and you've all registered for them, so I'm not going to go through those in any detail whatsoever, because you already know what you've signed up for. This seminar series has been put in place to basically support our actions to talk to our clients and talk to our users, and also to inform people about all the wonderful things that are happening at ANFF that they might not normally get a chance to be exposed to. We were hoping to do this in a showcase forum where we would get everyone together and we'd have a good day talking about all the different types of projects that we have ongoing. But unfortunately, COVID has meant that we've had to curtail it to pick the best of the best and put them in front of you on a webinar instead. So that's what we're going to do. Our in-person event has been moved and it is still going to happen. So we're hoping to do that in Melbourne next May. So make sure that you've got some space available in your diaries to come down to Melbourne and listen to some of the incredible things that are happening around the country at ANFF facilities. Couple of housekeeping notes. We are going to run this through Zoom webinar, as you all now have logged into. We're doing the Q&A through the Q&A button, so please write your questions down as you have them. We'll hold all the questions until the end of the talks, and then I will put your questions to our speakers. If there's any that are left over, we will make sure that they're attended to and sent back to you. We are recording these, so please bear that in mind. I think that is, I think that's the last of my things that I have to say. So with that, I'm going to introduce our first speaker. It is Dr. Pradeep Annamale, and I'm sure I have butchered his name, my apologies, from the University of Queensland. Pradeep is a researcher who's involved in a project, a very, very interesting project that is a collaboration between UQ and an Indigenous corporation in northern Queensland. And they're partnering to find the industrial applications for a natural grass found in Queensland. And I'm sure Pradeep is going to give you much more information on it as I hand over to him. So thank you, Pradeep.
Thank you, Jen, for your kind introduction, and yeah, I'll take you through that. Start sharing this screen. Okay. Thank you, Tom and Jane, for giving me this opportunity to talk about our work, mostly on the spinifex nanofiber. And today I'm literally focusing on the construction material, building construction materials. They are from the spinifex. Okay. So before going into the topic, I'll explain a bit of our group background, so what we are good at. And we are good at making nanomaterials, different nanomaterials, starting from inorganic and organic, clay, nanocellulose, from lab scale to pilot scale, and also we are also good at the processing polymers, plastics, doing lots of injection molding and compression molding, and testing their properties, mechanical properties and thermal properties and other things. So this is our a brief background. And so what today I'm going to talk in terms of towards actually the sustainability. So we are in the, especially after this post-COVID situation, we have to look for our lifestyle and the how we utilize the material, how we exploit the sources. So towards we have to think about the sustainability. And this in the sustainability there are three factors: environment and economy and society. So where and the UN has also set up the development goals by that we have to achieve by 2030. So our most of our research are aligning to that development goals. So what we are good at is the materials. So from material points of view, the sustainability is all about making the materials that are accessible to almost the wider community. And so it will involve cost-effective processing, renewable raw materials, cleaner and greener processing, and probably the less materials and energy consumption, and the materials that have renewability and recyclability, and low or less or no environmental impact, and most importantly, the having the performance during the service life, and so that, and also the improving their service life. Okay, so these are from my point of view actually on the materials towards sustainability. I think in this way. So what I'm focusing on is the building materials for future. Okay, for so which involve mostly the lightweight and also the more renewable materials, more greener materials we talk about, and less processing. So there are different materials like cement, concrete, and geopolymer, foam plastics, and what you're seeing in background in my slides are about those different materials. So today I'm going to concentrate on cement and concrete. And so we use we are looking at the making nano materials from the renewable sources. So the cellulose is the most abundant building block that is available in the nature, in the form, in the plant, and even in some of the marine animals. So in the plant, when you look at the plant cell walls, so if you deconstruct from the plant cell wall, so that has actually the polymers, which is called lignin hemicellulose. And then if you go further and further closer to the nanoscale, so you have cellulose as a crystalline material embedded in the hemicellulose and lignin matrix. So if you deconstruct back into this nanoscale, so we can exploit the the mechanical property that offers, and also the chemical functionalities that it has the OH groups, and it's a linear polymer. So we can exploit this functional groups and the mechanical properties. And this is it is really low density in comparison to other inorganic materials. And also it's when you go to the nanoscale, you increase the surface area, and you are making more hydroxide groups available for any functionalities. So these are kind of attributes of nanocellulose, where it's renewable, and we can actually make different shapes and different morphology of fiber. For example, we can reduce it to nanocrystals, so rod-like nanocrystal, or filament-like fibers. And with the classical organic chemistry, we can modify the surfaces as well. And it's, as I discussed earlier, it has the high mechanical properties at really low density. Because of this, actually, it has really wide range of applications, starting from personal care, even industrial applications, to automotives and aerospace. It's a large area that we can cover with this small nanomaterials, and the demand for it's increasing. So we can actually we can get nanocellulose from any biomass resource. It's not that much difficult. Okay, so what is a unique thing about the Australian spinifex nanofiber? So the spinifex was it has actually grown. You can see in the Australian map in the northern part of Australia is an it has survived for million years, 15 million years. And in the extreme conditions, it has evolved that very unique structure or a leaf anatomy, so it has to survive at really hot conditions up to 55 degree or something. So what it does is actually when it is dry conditions, the spinifex grass leaf actually closes tightly, and that holds the water inside the leaf, and it survives. And also it has the root that has goes into the land up to a few meters. Okay, so that's why it is actually when it gets raining and then it resurrects back, and you can see that it grows really well in this desert. So it opens the leaf to evaporate humidity, moisture, and so it has the very unique structure, which makes actually easier to defibrillate or deconstruct back into nanoscale. So this is a very unique morphology. So we can get, that's what you can get nanocellulose from any resource, but so this kind of unique morphology makes it really easier for getting the nanofibers. So the other thing about the lignocellulose resource, where we have lignin, hemicellulose, and cellulose, we can actually tune the composition internally, and also in the bulk and also in the surface. So what it actually implicates that when you have a high amount of lignin, it becomes less hydrophilic. When you remove completely about the lignin and hemicellulose, it becomes more hydrophilic and polar. So that kind of the functionality we can change. That's one thing that we can have, and especially the non-wood biomass sources has the higher amount of hemicellulose, which are kind of thermoplastic polymer, which makes that fiber to be tough and flexible. So they actually you make actually a tough paper that we can make from this nanofiber. And when so this was it was in 2013 we invented this fiber. And because I come from the background on the CNC, which is rod like nanocellulose, and when we saw this one particularly, so we are so much excited about that much of the toughness that we could get with the nanofiber. So that's where actually we went into protecting IP. So when we compare that the nanocellulose, spinifex nanocellulose, against other the examples. So the nanocellulose, the rod-like nanocellulose stays at higher high cost, because you need to treat with acids or oxidizing agents to get that nanocrystal type. Or if you want to have a nanofiber, something like this, you have to do other oxidizing treatments. So our spinifex actually, without any such treatments, we could get that long and thin nanofiber and tough nanofibers. So we started around 2012, and now we are we got few grants from federal government and state government, and we had a partnership growing in this last 8 years now, and now we are fully operational as a pellet scale. So we can produce the nanocellulose about 5 kilo a day. So we have plant downstairs, and it's not actually about, it's not only about the the making materials, nanomaterials. It's more than that. So we have the indigenous partnership and training, okay, that and plus all these material applications, starting from recycled paper as a, and where we can increase the improve the strength of the papers with just by adding few percentage of nanofiber, and the cement strength, and also the elastomers, rubbers, gloves and condoms. So these are the products that we can improve their performance and durability of these materials. And with that, so we had under the EQDAC, the Digulangi Aboriginal Corporation umbrella agreement. So we share the commercial benefit to the indigenous community, and for this partnership we also got some recognition from EQ and our. So we also train, you can see here, so we also train most of the the downstream process, from the screening, cutting the grass, making, washing, and making the pulp, then making the nanofiber. So they so we train very often. So we had a few visits from indigenous the trainees. So today I'm going to talk about the one of the construction material, which is cement. So it's actually, you can see here in the process, it involves the minerals mining, so exploitation, plus the grinding and heating to really more than 1,000 degrees Celsius to get calcium oxide and silicon oxide, silica, okay, or alumina. So you start from the the minerals that you start, and you heat it to get oxides. So you get actually powder, micro scale powder. Okay, so when you add water again with where it becomes adhesive and to make that uh, stronger material. Okay, so this is uh, a bit of basic on the making cement material. But actually, when you look at this, particular the process, it involves green gas emission. Okay, so and we are using the cement and concrete, that actually helps us to improve our lifestyle. But and it is going to increase the consumption of the cement, and with the increasing population, so we need materials there. And also, but it is associated with the greenhouse gas emissions. And to reduce that, reduce the metal consumption in the cement and concrete. So what we can do is improve their durability, or improve their performance, and so that we can reduce the maintenance cost, and also reduce the amount of material that we use. Okay, so this research on the nanocellulose for adding into cement has been for a few years now, and the mechanism, there are two types of mechanisms actually involves in improving their properties. One is where we have so what you're seeing here is the black particle is the dry cement particle, where you can add the nanocellulose that can actually go on surface on the of the particle, and when you add water, it can act as a network for water penetration and further hydration. So what you are seeing, the gray part area is the hydrated area. So that's what is actually the giving us the strength and the and also the the adhesive property. Okay, for so that can hold the whole aggregates that you are adding, sand and stones. So we want to enhance that hydration. So that's one mechanism. The other mechanism is where if we add nanofibers, so the nanofibers can, because it's nanoscale, and it can actually mend actually act as a fiber reinforcement. Okay, so at nanoscale. So there are two mechanisms that involves in improving the cement properties. And for for mainly for cement, actually we can increase that few mechanical properties, like the compressive mechanical property and flexural. And so for compress strength, we can increase the compressive strength by adding bit of more cement into it. But for flexural strength is actually a challenging one. Okay, so that's where actually our industry partner, which is TMR, so they were interested in improving the flexural strength. So we started with actually the simple cement, which is actually the type 1 cement, which is general purpose cement. And we tested actually about 6 types of nanofiber with different surface chemistry, where we did oxidation, acid hydrolysis to get different surface chemistry. And we got really good properties with the oxidized and acid hydrolyzed nanofibers, about 25% improvement in the flexural strength of just the cement. Okay, so and then we also tested with the sand and fly ash, which is another, it's a mortar. So we got up to 20% improvement, and this was done actually at the lab scale processing. And then we were trying to scale up this process. Okay, so then we tried this in the large scale, and with addition of you have the recipe here, which is cement, fly ash, and fine sand and water plus plasticizer. So we added only 0.25 volume percentage of CNF in this, and we tested the different processing variables, like varying the scale of the the nanofiber making HPH, which so homogenizer, and then the versus to the pilot scales that we have, and also this different walls within, which involves in the homogenizer, okay. So with the different length, they all actually affect the fibrillation efficiency. What I mean is that because this the pulp, when you get the pulp after the mild alkaline treatment, sodium hydroxide treatment, you get the pulp which is bundles of nanofibers. So you need to apply the shear treatment so that you get the nanofiber. So that actually it looks simple, but it involves actually the several variables to get that better well defibrillated nanofibers. So that's where we varied all this, and so they actually influenced our property. So these are the different variables. So when we compare actually about the lab scale and pilot scale, so what we are seeing is in here. So it's where we needed to go for higher number of passes and the more time of homogenization. So that's what we are seeing here. So it's taking from 9.5 MPa to 11. So this is it's not great improvement when we went into pilot scale. Okay. And so this was at motor, and it's at large scale, and this we tested with one of the industry partner here, and then we had to change our valves in that. So then we had to repeat it, and we get that improvement back, on the the 20% improvement. So then we also tested at adding an accelerator, because these five up to this, actually this is only the fiber which is less processed. What I mean is that you have the treatment of sodium hydroxide, and then that went in directly into the mechanical treatment to get nanofiber, and no other additives added. Okay, so that actually we learned that reduces the rate of curing, or hydration, and so we promoted that curing by adding an accelerator. So that actually helped us to so that's what we are seeing here in this graph. So we could improve that strength of the motor about 18% back. So these are the large scale um, um, plotting. So we could improve that even in the large scale processing. So that's what about the adding the nanocellulose um, in the construction material. So nanocellulose itself, I can say that actually nanocellulose itself is the versatile and functional material, because we can do lots of chemistry and the physical morphology changes. And spinifex is unique, and it is endemic to Australia, and have unique properties because of its the leaf anatomy, and various high hemicellulose layer content. And that actually helped us to look into wide range of materials, starting from soft materials to really rigid materials like our cement and concrete. And I acknowledge our the partners and the support from the both federal government and state government, and especially for my Advanced Queensland Fellowship. And I also acknowledge support from my team members. And thank you for your kind attention today.
Thank you very much, Pradeep. I think that was a whirlwind tour of a very interesting technology that's coming straight out of the deserts of Australia, through a partnership with universities, and getting that indigenous knowledge and turning it into something that is really useful in the real world. So if I can, if you have any questions, please send them through now on the Q&A. But first off, I will take my questions. So first of all, Pradeep, you mentioned that this is great to strengthen everything. What is it about the cellulose nanofibers from these particular grasses that make them so much stronger than everyone else's?
Actually it's about the resilience of this. I would come from the indigenous background. This plant is the symbol of resilience in the Aboriginal community. Okay, and it can withstand, and it can resurrect back, and to the extreme conditions. It is almost same when you process into the mechanical treatment, which is the high energy, high pressure homogenization, which is kind of shearing these bundles of fibers, and you don't need chemicals to shear that. Okay, and also if you whatever that mechanical treatment that you applied, the hemicellulose that is embedded in the between these cellulose crystals are acting like shock absorber, so it doesn't damage the fiber. Okay, so you get that long and thin fiber retained. So that actually, when you form a paper, so you get that tough paper, because it, you know, the hemicellulose, it's kind of a plasticizable material, and the cellulose crystal is, you know, the rigid material. So when you make any, you know, fiber or paper, so they are actually stronger, and it behaves like any semi-crystalline polymer that we can get.
Great, thank you. And another question I have. How much grass is required to produce, say, 1 liter, or I'll say 1 kilogram, because I know you get it in the solid form, of the nanocellulose, and how quickly does the grass grow back after harvesting?
So we are looking into that. Plus, in terms of production quantity, so it's about 60%, 60 to 70% yield from the dry matter. So
okay, so quite a lot.
Yeah, it's quite a lot. Unless you don't do any other chemical treatment, as I mentioned, like oxidation or acidolysis. You can do, but I don't recommend it for non-wood cellulose like spinifex. So for such acid hydrolysis or that kind of chemical treatments, we can do in wood like bulk materials. So these are a bit unique. So we want to exploit that property. You want to retain that long and thin, high aspect ratio. So it's with less chemical treatment, you get that property. So that's enough, I think.
Great. And very quickly, if you would, how do the mechanical properties of nanocellular cement change with the Portland cement particle size? So if the cement particle size changes, how does the nanocellulose deal with that?
Yeah, actually, it would change because of its, the hydration efficiency. I think most of the cement particles are micro sized, so 50 to I think 80 micro size, and even some of them are up to millimeter. But the hydration is the key, and you don't want to have unhydrated portion. Okay, if you imagine that spherical particle of cement, and you don't want to have the unhydrated particles, which is actually, they call it calcium silicate gel, hydrate gel. So you want to form that, so we want to form that kind of fully hydrated gel to get better properties. So the CNC or Nanocellular helps for that.
All right. Well, thank you very much, Pradeep. And on behalf of all of us at ANFF, I would like to thank you for agreeing to do the talk and for providing us an insight into this wonderful technology. So thank you. I'll now move on to our second speaker of the day. If I can pull up the right screen, which I probably can't. There we are. So our second speaker today is Professor Mick Whitford from Macquarie University. Mick is a node director with us at our ANFF OptiFab node, and has been working with vast numbers of technologies in the optical sciences for many, many years. What he is currently going to talk to us about is sensing in the construction space, and how the rollout of good, robust, and reliable sensors can assist us in construction. So with that, I will pass over to Mick for his wonderful talk. Thank you.
Very much, Jane. Okay. Right, we all see that? Fantastic. So Jane probably gave a better title for my talk than the one I've landed on here, because I couldn't for the life of me remember what title I gave Jane. So I decided to go with something a little bit provocative, because I get concerned that the buzzwords, Internet of Things is an overly used and abused term. I see it appear a lot in project proposals that I review, and often when I dig down and actually challenge the people on what they're proposing to do, it's not clear to me they actually understand what they want to sense, how they're going to go about sensing it, and indeed whether fit-for-purpose sensors are even available to solve the problem they want to solve. So just quickly, in the next 50 minutes or so, I want to walk you through the journey that we've taken in this sensing space to deal with that three-pronged problem. So this is all about how ANFF has actually supported activities such as this. So there may be some in the room who remember that in 2015, ANFF embarked on a national roadshow where it went to every national city, giving talks on our capabilities, talking to industry partners and academic partners, and trying to actually gauge interest. And I actually I attended many of those with our CEO at the time, Rosie Hicks. And at one of those, particularly one in Sydney, these people at the back of the room came and approached me after the talks, and they're from Sydney Water, and they presented me with this problem that Sydney Water actually spends $60 to $80 million on maintenance, a lot of which goes into wastewater systems. And they had a strong interest in better asset management techniques that would help them with predictive lifetime assessment and help them actually use their maintenance budgets more efficiently. This is actually a national problem. So it's about $1 billion nationally that our water utilities spend on maintenance. And as you can imagine, globally, it's many, many billions of dollars. So the real problem they have is this one, third bullet point there, that when they use conventional humidity and temperature sensors in their wastewater systems, they would at best last 1 week, 2 weeks at most. And so the problem they put to us was, could we actually come up with a long-lived and cost-effective sensor? And long-lived in this case is something that will last for years. So just use OptoFab and ANFF as the jumping off point. But I often like to say that OptoFab actually bridges the gap between conventional milling and machining job shops. And on the left-hand side there, I show the smallest drill bit you can actually buy, which is 120 microns in diameter. So it's the smallest sort of feature you can actually have made for you in a conventional job shop. And in there is a tiny little hole, which is laser machined. And that's sort of nicely illustrates where precision microfabrication, laser microfabrication comes into play, where we bridge that sort of what conventional job shops can do and go all the way down to where then the lithography sort of picks up when you want sort of nanometer resolution. This laser microfabrication will get you to about approximately 1 micron resolution, but over a relatively large footprint. But perhaps the key thing is we're agile with respect to materials we can actually process. So we equally do metals, polymers, glasses, and crystals. We're agile with respect to geometry. So 1D, in this case, fibers, 2D, wafer surface processing, and indeed 3D, as shown that top right-hand image there. And that also makes us very agile with respect to the applications we pitch at. So OptoFab has loosely 3 basic thrusts to its capabilities. There's subtractive fabrication or top-down, additive fabrication or bottom-up, which we're all familiar with in these new 3D printing facilities, and something that I like to call material modification or inside-out processing, where we actually use lasers to actually modify the material properties of transparent materials in particular, be it polymers, glasses, or indeed crystals. And our sensing work actually draws on all 3 of those capabilities, and you'll get a sense of that as I go along. So back to Sydney Water and their problem, and it's not just Sydney Water. So the discussion started with Sydney Water, but Melbourne Water actually joined up midstream. And this is the shared problem they have, and indeed water utilities around the world, that in wastewater pipes, particularly in the air volume, you get the hydrogen sulfide gas, which in high humidity environments and with a little bit of bacterial action gets converted to sulfuric acid, which corrodes the concrete, actually turns the concrete into gypsum, and actually can eventually expose the reinforcement bar in the concrete and compromise the integrity. So the items of interest for us with respect to monitoring the formation of sulfuric acid, humidity, temperature, hydrogen sulfide, of course, in the airspace, but also a strain and a pH front moving through the concrete itself as indicators of an corrosion event about to happen. This is what happens. This is how it manifests, concrete corrosion in wastewater pipes. You can see in the ceiling of that wastewater pipe that all the aggregate is actually exposed as the concrete that will normally cover that has been eaten away. And ultimately over time, the aggregate will fall away as well and eventually expose the rebar. And at that point, teams of people have to go down to great expense and rehabilitate that section. And this is an example of some of the tests Sydney Water do, and Melbourne Water do, where they actually test concrete samples, try and make them more resistive to this corrosion problem in wastewater sites. So the approach we took was something Sydney Water had already tested and shown to actually have durability in this space. So it's using optical fibres, which survive well in corrosive environments. This is where we use the unique capabilities of ANFF to use our inside-out processing to write brag grading structures directly inside the core of off-the-shelf, commercially available glass fibres. And by making these periodic features with a certain period that's tuned to a particular spectral wavelength, as shown on that right-hand bottom graph there, we can make little sections with unique spectral fingerprints that will tell us something about the local changes that fibre has been exposed to. Particularly as shown here, if then we have put a transducer around some of those little brag grading features. In this case, a transducer based on polyimide coating. Polyimide is hygroscopic, so it will actually swell in a linear fashion with respect to humidity, and it's reversible. So the act of that polyimide coating swelling with humidity causes the period of the brag grading to change. The spectral features I showed in the previous view graph will actually move as a function of humidity. And we can calibrate against that and actually have a real-time sensor. And there's some of the metrics at the bottom there. So we see about 10 picometers shift per degree Celsius and 1.8 picometers per shift per percent relative humidity. Packaging is a big deal because we are in quite a hostile environment that's subjected to flooding events and all sorts of stuff flowing down these wastewater pipes. So we've invested a lot of time and energy coming up with clever 3D printed packages with little porous sections and often internal chambers to help with functionality. And ultimately, we have to keep in mind that Sydney Water, Melbourne Water and others actually want to deploy these in future in large volumes. So everything we actually embark on has to ultimately be scalable and scalable at low unit cost. And so our target here is below $30 per sensor. Now we also have to know what we want to sense, particularly in the concrete. So we've done a lot of work with ANSTO doing neutron beam tomography on concrete samples that we put through accelerated aging, accelerated acid corrosion tests. And as we scan through this concrete block and that animation there, you'll see this sort of black ring appear a few millimeters inside the surface of that cylindrical section. And that's actually an iron ring, which tells us there's actually species migration that happens inside the concrete during this corrosion process. So it's these sort of tests that sort of gives useful insights into how the corrosion front moves through the concrete, and indeed, what are the sort of things we need to test that tells Sydney Water and others that actually have a problem. And neutron beam tomography is also great, actually telling us whether the sensors are actually acting as we think they're acting. Are they actually measuring a fluid front moving through the concrete? So we've actually done real-time monitoring as watching the fluid front move through a concrete sample that actually has one of our sensors embedded in it. And so on that left-hand image there, the cross cutaway section, you can actually see cross-section through one of our grading features, our probes, relative humidity probes. You can just barely see the fibre there at the very bottom of that probe. You can see the sort of porous section in the 3D printed section. But what we noticed is as the fluid front moves through that sample, it will actually wick around this particular sensor, and the sensor will detect nothing. So again, this told us a lot about the strategies we had to develop with respect to implementation and installation of these particular sensors. So this resulted in two strategic approaches that we have invested in. So one is actually having sensors that can be deployed in the air volume of these wastewater pipes. And I'll talk a little bit about those in the next few view graphs. But also, with respect to inside the concrete, we knew that it was never going to be feasible that contractors could be trained effectively to actually install these inside the concrete in a fashion where the calibration will be meaningful. So we've actually taken an approach. We're going to use smart concrete coupons as almost a sacrificial corrosive feature that will be bolted on the inside of the glass of the concrete pipe. So on the field testing, now this is certainly not a sexy area that we work in. These are the sort of sites that my team members have to frequent as part of their testing. So this is a test site out at Manly somewhere. And indeed, in that little purple circle there, you can actually see some of our sensors dangling down into this particular pit. And they were actually installed there for 10 months. The plan was to do it over 12 months, but some contractors turned up one day and actually traced our sensors. But certainly that 10th month period, they actually survived a number of flooding events. There was issues with nappies and baby wipes actually wrapping themselves around the sensor. But they performed as expected all the way through those sort of nasty cycles. And this is what the data looks like. So it tracks well. We had sensors outside that particular pit as well, and we were tracking them against the Bureau of Meteorology data, and they would certainly follow that accurately. And indeed, you can sort of see reliable information there. This is just taken over a few months in this case, but certainly the sensors worked as we had hoped over a 10-month period and survived a number of biofouling events. With respect to our smart coupons, so this is what our smart coupons look like at this moment. So again, we're making these in a calibrated fashion. They're installed, so we know that the sensors will actually interact with the corrosion front, moving through the concrete block itself. We've done various tests, such as shown here. We can actually dip these in water and actually look at the moisture front as it actually tracks through a concrete block. And indeed, we're actually building on that by developing strain sensors as well. We can actually look at the concrete as it starts to break down, as acid attack will actually eat away at the concrete itself. And indeed, even look at the effect of pH even before that corrosion event starts to happen. And so we're developing pH sensors as we speak. And these are some of the examples of the pH sensors we've tested today. And again, you can see from these that there's sort of a sophisticated arrangement of these fibre brag rating sensors that we make in-house, coupled with these quite sophisticated 3D printed packages. So, as I said before, this is certainly not a sexy area to work on, and it's certainly not, it's hard to excite people about working with sewer pipes and wastewater systems. So why do we do it? Well, as we started to dive into this area, we realised that this was actually bigger than just Sydney Water and Melbourne Water. So we had a lot of the transport industry sector actually reaching out to us as well, interested in actually deploying some of our fibre sensors into motorways and things of that type. All of which actually seeded this idea, which again came out of our linkage project with Sydney Water, and indeed which was all seeded by the original ANFF Roadshow back in 2015. So we started on this CRC journey. We put a CRC bid in last year, and in that bid document, ANFF features heavily. And we were fortunate enough to be told December last year that we were successful. And as a result, the Smart Grid CRC has been rolled out this year. So we're just a few months into our life cycle. And although our original thinking was this was going to be the Smart Grid, the CRC, wasn't called Smart Grid at the time, but the CRC would be mostly based around asset management. As we spoke to the construction industry in particular, we realised it was bigger than asset management, and so expanded to actually include other aspects of the concrete life cycle, including sustainability, which is an area that the previous speaker, Prateep, actually touched on today, but also engineered solutions as well. So we have a list of industry partners that are all going to keep my smart sensing group busy for quite some time to come, as we actually explore other sensor applications, all of which will continue to benefit from the strong support of ANFF. So they're just more of our partners, university partners in particular. And with that, I'd just like to wrap up by, again, acknowledging the very strong support we've had ANFF actually helping us meet with Sydney Water at the very outset, and indeed helping us along this journey, actually developing fit-for-purpose sensors that would actually outlast the competing sensors at the time, which would only last a few weeks, and indeed act as a springboard for a suite of ongoing sensor development and new applications that we're pursuing. So with that, I'll stop and I'll hand over to you, Jane.
Thank you very much, Mick. And as always, when Mick speaks, you'll understand the amazing benefits of having ANFF in your back pocket, and also the things that, you know, the partnership between ANFF researcher and finding a problem to fix can really provide a really powerful way of moving things forward in a lot of different areas. So the floor is open for a couple of very quick questions before we close up. So if you have any questions, please drop them into the Q&A. When my first question to you, Mick, is when you first came across this project and you were talking about putting sensors into sewer pipes, how did the research group actually react when you said, this is what we're going to do?
Well, maybe I'll start with how I reacted. I was not thrilled about engaging at all. As you can imagine, this is not the sort of thing that you imagine is going to produce you nature papers and things of that type. It's a hard sell. And so even before selling it to my group, I had to sell it to myself. And it was what followed and transpired was a suite of meetings with Sydney Water. They sent me papers. I read the papers. And it happened over weeks where I started to sort of eventually have this light bulb moment, realize this is actually quite a compelling problem. It's not just putting sensors into sewer pipes. It's a global problem. You know, taxpayer money, a lot of taxpayer money goes to actually funding this, and it'd be great if we could explore some of that back. And I guess at the back of my mind was this sense that there may be opportunities outside of wastewater sensing as well, that were maybe a little bit sexier and palatable for my team. So yeah, selling to the team was certainly not easy. There's still disgruntlement when they're sent out to some of these sites to do these installations, but they recognise the long-term benefits that are coming through with Smart Creek CRC, where we get to potentially play with bridges and other more interesting structures as well.
It really does, it makes us reevaluate where the important things that we should be doing are. So, you know, there is that, you know, that we all appreciate the fact that we have indoor toilets that make stuff disappear. And the fact that we might have to put some extra efforts in to make sure that's a sustainable industry long term. You know, it's a really important thing, but not, as you say, not the sexiest of titles to start with.
Not the sexiest, and I had anticipated there'd probably be 0 papers that would come out of this work, but we've been surprised. There's been some fascinating chemistry, such as that iron ring I showed you in the neutron beam tomography work, which we've just preparing for publication. So it will actually produce a lot of probably very meaningful publications, despite my reservations at the time that it would not. So you've got to keep an open mind, is my point.
I've got one more question for you. So it sounds like this project is pretty much finished, or you've gotten to the point of providing, you know, a sensor, but what's your next step? Is it scale up?
It's scale up. So this is where now Smart Creek CRC will actually jump in the mix. So we've identified some impediments to scale up. So it's not around the sensors themselves, it's all the electronics associated with the sensors. It's actually establishing a workforce that can actually install these as well. So this is where CRC is actually focused on helping develop a workforce through TAFE and TAFE programs, building an ecosystem where we work with fibre contractors to do installations, and indeed continue to drive down the cost of some of those, some of the sensors themselves with some of the back-end components, optimise the way we actually feed the data into the cloud, and then actually process that data in a form that's palatable and triggers the right response for the end user sitting at his or her computer.
So by no means a completed project.
Absolutely not. No, it's only scaling up, and indeed that was what we saw with the linkage, that there was an opportunity to actually take this to the next level and so on and so forth. And that's just Sydney Water. Yeah, next week I'm talking to Transport New South Wales, because they want to actually ride on the coattails of the sort of stuff we're doing with Sydney Water and Melbourne Water, I should say.
Thank you very much, Mick. So with that, I will close out our first webinar. I'd like to say thank you very much to Michael and Prateek for their incredible insights into the works that they're doing at the moment at their respective projects. I'd also like to thank the sponsors that ANFF have attracted towards our showcase, which obviously isn't running, but they have rolled over their sponsorship and are maintaining their support through for this seminar series. So we do thank them very much for their ongoing support of what we do here in ANFF. So I'd like to just finish then by saying, if you've had any further questions or comments about what you've heard today, if you would like to invite more of your colleagues to turn up for our webinars in the coming 5 weeks, please do so. The registrations are still open and we still have space on our webinar platform. And next week we have two speakers. One is Gordon Wallace, who is another ANFF director from Materials, and we also have Anthony Brewer from a startup medtech device company called Wear Optimal, who are developing wearable technologies for sensing of different aspects of human biology. So those will be two very interesting talks next week. So I look forward to seeing you all then. Take care, and we'll see you then.